For most of recorded history, space was understood as a passive backdrop, a vast and unchanging platform upon which stars burned and planets orbited. Strip away every celestial object, and something would remain, an empty, eternal stage. This intuition held firm for centuries, until general relativity shattered it entirely. The theory revealed that space and time are not rigid scaffolding, but a unified fabric, one that bends, stretches, and warps in response to the matter and energy resting upon it. If the old conception of space resembled immovable hardwood, the relativistic version behaves more like a waterbed, deforming under every footstep. That deformability opens an extraordinary door. An elastic fabric can, in principle, be torn and reconnected in ways a rigid stage never could. Research into the mathematical solutions of Einstein's field equations has shown that certain configurations of curved spacetime permit tunnel-like shortcuts known as wormholes. Imagined in 2 dimensions, the universe resembles a vast sheet. Fold it just so, and 2 enormously distant points can touch, joined by a short bridge. A traveler crossing that bridge could, in theory, traverse the cosmos faster than a beam of light racing along the sheet's surface. The catch is significant. General relativity is a mathematical framework whose equations yield many solutions, and not every solution corresponds to something physically real. Wormholes remain theoretically permitted, yet observationally unconfirmed, existing so far only as tantalizing possibilities written in the language of geometry and gravity. The earliest wormhole solutions emerged from work by Albert Einstein and Einstein-Rosen in 1935. These Einstein-Rosen bridges reinterpret every black hole as a portal connecting to a mirrored parallel universe. The picture unfolds logically. Compress an object until space-time curves so severely that it collapses, and a one-way boundary forms, the event horizon. Anything crossing inward is trapped, drawn inexorably toward the central singularity. But one mathematical possibility replaces that singularity with something astonishing. The interior of the black hole opens into another universe, an inverted mirror image where time runs backward. In this mirror cosmos, the counterpart of a black hole is a white hole, an object that repels rather than attracts, spewing matter outward in a process reminiscent of a localized Big Bang. A 2023 study explored quantum corrections to Einstein-Rosen bridges and found that quantum gravity effects could replace classical singularities with bounce regions, lending theoretical support to white hole models. Despite the elegance of this picture, Einstein-Rosen bridges are fundamentally non-traversable. Crossing one requires infinite time, and the bridge pinches shut before any traveler could pass through. Entering a black hole connected to a white hole would not deliver you to another universe. It would deliver only death. For practical interstellar travel, physics demands a fundamentally different architecture, a traversable wormhole, one that remains open long enough and wide enough for a spacecraft, or at least a signal, to survive the journey. If string theory, or one of its extensions, accurately describes nature, the universe may already contain a hidden network of traversable wormholes woven into its fabric since the earliest moments of existence. During the first fractions of a second after the Big Bang, quantum fluctuations at scales far smaller than an atom could have spontaneously generated enormous numbers of microscopic wormholes. Threaded through these tunnels, according to certain string theoretic models, are one-dimensional defects called cosmic strings, remnants of phase transitions in the infant universe. These strings would have stabilized the tiny passages. During the explosive expansion of cosmic inflation, the endpoints of these wormholes would have been dragged light years apart, scattering potential portals across the cosmos. Research published in 2024 examined whether primordial wormholes threaded by cosmic strings could survive to the present epoch, concluding that specific string tension values would permit long-lived structures. Intriguingly, from the outside, a wormhole mouth and a black hole can appear nearly identical. This resemblance has led some physicists to hypothesize that the supermassive objects, anchoring galactic centers, including the Milky Way's own Sagittarius A star, might be wormhole entrances rather than conventional black holes. A 2024 analysis outlined specific observational signatures that could distinguish wormholes from black holes, including subtle differences in photon ring structure. The wormholes may already exist. The challenge is recognizing them. Constructing a useful wormhole requires satisfying three non-negotiable engineering criteria. The tunnel must connect genuinely distant regions of spacetime. It must lack event horizons so that two-way travel remains possible. And it must be large enough that tidal gravitational forces do not destroy anything passing through. The greatest obstacle is stability. Gravity naturally acts to squeeze any wormhole shut, pinching the bridge until only disconnected black holes remain at either end. Holding the passage open demands something extraordinary. Exotic matter. Exotic matter is not ordinary matter, not antimatter, and not dark matter. It is a hypothetical substance possessing negative mass and negative energy density. While positive mass generates attractive gravity, negative mass would generate repulsion, a kind of anti-gravity capable of propping spacetime open against its natural tendency to collapse. The quantum vacuum, the seething ground state of empty space, constantly generates and annihilates virtual particle-antiparticle pairs. Through the Casimir effect, two closely spaced conducting plates can manipulate vacuum fluctuations to produce a region of negative energy density between them. A 2023 study demonstrated refined Casimir measurements consistent with predictions, reinforcing that negative energy densities are physically real at microscopic scales. Whether this phenomenon can be scaled up to stabilize a macroscopic wormhole remains deeply uncertain, but the principle that spacetime can be manipulated through quantum effects is no longer purely speculative. Imagine a network of stabilized wormholes with one end orbiting Earth and the other flung into deep space, creating a hub connecting a human civilization, spread across light years, yet only a doorstep apart. The vision is exhilarating, but nature may have installed fundamental safeguards against it. Opening even a single traversable wormhole threatens to break the causal structure of the universe by enabling closed time-like curves, paths through spacetime that loop back to their own past. In plain language, wormholes could create time travel paradoxes. Stephen Hawking formalized this concern with his chronology protection conjecture, proposing that the laws of physics conspire to prevent time travel on macroscopic scales. Subsequent work using semi-classical gravity suggests that quantum energy buildup at a wormhole's throat would destroy it the instant it approached conditions, allowing time loops. Many physicists interpret such results as evidence that traversable wormholes are not merely difficult to build but fundamentally forbidden by nature. Yet the debate continues. Recent developments in quantum gravity, particularly connections between wormholes and quantum entanglement, suggest that wormhole geometry may underlie the very structure of quantum information. For now, wormholes live in equations, in thought experiments, and in the stubborn human impulse to ask whether the universe's geometry might, just might, contain secret doors waiting to be found and opened.